Today on Macaulay Math, we're talking the chain rule. Intro. Okay, good day. I am Professor Macaulay. This is Math 200, Calculus 1, Lesson 9 on the chain rule. Our goals for today: we're going to find the derivative of a composite function using the chain rule. We're going to find the derivative of a function using the general power rule. We're going to simplify the derivative of a function, and then we're going to find the derivative of a trigonometric function using the chain rule. The composition of two functions can pose interesting challenges to the process of differentiation. The chain rule provides a solution to these challenges by giving a shortcut, provided that we can break up complex functions into a composition of simpler functions. The purpose of this lesson is to see those compositions and make the process of differentiation easier. Let's get started. First, we're going to start with a precalculus definition. The composition of two functions, f and g, produce a new function h that is the result of applying the result of g function into the f function shown by the expression h of x is equal to f composed with g of x, which is the g function plugged into the f function. As a quick example, the composition of f with g, given that f of x is x squared and g of x is equal to x plus 2, f composed with g of x is equal to f of g of x. And so I take that g function and I plug in the expression that is the g function into f. And then since the f function is squared, we're going to take this x plus 2, we're going to square it, and then we're going to distribute to get x squared plus 4x plus 4. The chain rule basically says this: if you have a composition of functions, then the derivative of that composition is the derivative of the outer function, leaving the inner function alone, times the derivative of the inner function. Or the derivative of y with respect to x is the derivative of y with respect to u times the derivative of u with respect to x. A link to the proof can be found in the comments below. The general power rule: this is a simple application of the chain rule for a function raised to a power. So if I have a function that I'm raising to a power, then just like the simple power rule, I can bring that power down front. I can reduce that power by 1, leaving what's inside alone, and then multiplying by the derivative of what's on the inside. Again, if you take the derivative of some u function to a power with respect to x, then we can bring that exponent down, reduce the exponent by 1, and then multiply by whatever the derivative of u is with respect to x. So let's talk about a first very simple example of the chain rule. But before I can take the derivative of f of x equals the square root of 9 minus 4x, I have to rewrite this function. Using a rational exponent. Now, we know that the square root function can be rewritten as 9 minus 4x to the 1/2. And so when I say that this is a composition of function, and I'm not going to write this every time, but I'm going to say that my quote-unquote inner function is this 9 minus 4x, and then I'm going to say that the outer is going to be just x to the 1/2. So now, when I want to go and take the derivative of this thing, I'm going to apply the general power rule, which is an application of the chain rule. And I'm going to take this 1/2 and I'm going to bring it down in front. I'm going to leave the inside of that function alone. And then I'm going to reduce this exponent by 1. So a half minus 1 is going to be negative 1/2. And now I have to multiply this by the derivative of what's inside. Now, 9 minus 4x is an easy derivative. It's just negative 4. But I should simplify this function. And so some simplification, let's say we push this negative exponent to the bottom, and then the 2 cancels with some of the 4 there, and I get a 2 to cancel out of the 2 and a 2 to cancel out of the 4, leaving a 2, and then it is just going to be 9 minus 4x to the 1/2. And that is my final answer. All right. Trig functions in the chain rule. If I take the derivative of sine u with respect to x, then it is going to be equal to the cosine of u times the derivative of whatever u is. And if I take the derivative with respect to x of the cosine of u, it's going to be negative sine of u times the derivative of whatever u is. So let's do a real quick example here. And so when I look at this first one, I have the outer function being the sine function, and then my inner function being this 2x to the third. So the derivative with respect to x is going to be the derivative of the outer function. So the sine u becomes cosine u. So I do cosine, and I leave the inner function alone, 2x to the third, and then I have to multiply this portion of the derivative by the derivative of the inner function. Now, the derivative of 2x to the third is just 6x squared. And I'm going to rewrite, just so that I remember not to take the cosine of the whole thing, I'm going to rewrite this as 6x squared cosine 2x to the third. And that is going to be my solution to that particular problem. Now, if I come over here and I do this derivative, you notice that I have this square on the outside, I have the cosine, and then I have a 3x on the inside. So this is really the composition of three functions. The outermost function being the squared function, the middle function being the cosine function, and then the innermost function being the 3x function. And so I can apply the chain rule. I'm just going to have to do it twice. The general power rule says that I bring the 2 down and I leave what's on the inside alone. So cosine of 3x, and then I reduce the 2 by 1, so I'll leave a 1 there, times the derivative of what's inside. But the derivative of what's inside is cosine of 3x, which is a composition. So I have to take the derivative of the cosine part. That becomes negative sine of 3x. But now, because this cosine 3x is also a composition, I have to multiply by the derivative of the innermost value, which is 3x. So the derivative of 3x is just 3. Now I would like to simplify this if I can. I've got a negative, I've got a 2 and a 3. So I'm going to write this as negative 6. So negative 1 times 2 times 3 is negative 6. Cosine of 3x times the sine of 3x. My next example, evaluate the derivative at a given point. And so we want to figure out what the derivative is at this point. And so essentially what we're going to do is we're going to find the derivative of f. We're going to plug in 4, and then that will be the value of the derivative. So let's rewrite first. We are not doing the derivative yet, so it's still f of x. But I'm going to rewrite this as x squared minus 3x to the negative 2 power so that I can apply the general power rule. All right, so now I'm going to do the derivative, f prime of x, and I have a composition of the x to the negative 2 power is my outer function, and then my inner function is this x squared minus 3x. So I bring the 2 down, I get my negative 2. I leave what's inside alone, so x squared minus 3x. I reduce the power by 1, so negative 2 minus 1 is going to give me negative 3. And then I multiply that result by the derivative of what's inside. So the derivative of x squared minus 3x is 2x minus 3. Now normally I would say that you should reduce this function, get rid of that negative exponent. But remember what this question is asking us to do. It's asking us to evaluate at the given point. They're not asking for the derivative, they're asking for the value of the derivative. So we have this function at a point where we can actually use it. And so I'm just going to, at this point, go f prime of 4 is equal to negative 2 times 4 squared minus 3 times 4, all to the negative 3 power times 2 times 4 minus 3. And I'm going to evaluate that. Okay, so now let's evaluate this. On the inside, I have 4 squared is 16 minus 3 times 4 is 12. So 16 minus 12 is going to be 4. And so I'll have negative 2 over 4 to the third. Now 4 to the third is 64. That we're going to multiply by. 2 times 4 is 8, minus 3 is 5. So I'm going to multiply by 5. So I'm going to get negative 10 over 64. Now I can take a 2 out of both of these two values, and that'll give me negative 5 over 32. And that is going to be the value of that particular derivative. Okay, find the first derivative of this function. So I, again, am trying to show that you can have composition of multiple functions. Here, my outermost function is going to be the x to the third function. My inner function is going to be this 2 plus the quantity to the fourth, and then my innermost function is going to be this x squared plus 1. And so the derivative of this function, I'm going to apply the general power rule to this outermost function, so it will be 3, leaving the inner function alone. So I'll have 2 plus x squared plus 1 to the fourth, and now I reduce this 3 by 1, leaving me to 2. Now I have to multiply that by the derivative of what's inside. Now the derivative of any constant is always going to be 0, so now I just have this x squared plus 1 quantity to the fourth power. Again, I'm going to apply the general power rule and write that as 4 times x squared plus 1 now to the third power. And then I have to multiply that by the derivative of what's inside. So the derivative of x squared plus 1 is just 2x. Now there's not a whole lot that I can do with this other than to collect these values out front and say that maybe I have, let's see here, 3 times 4 is 12 times 2x would be 24x, and then I have this 2 plus the quantity x squared plus 1 to the fourth all squared times the x squared plus 1 to the third. And that's what I have right there. Well, that's all I got for today, folks. So, the Star Wars fun fact of the day. The post from an old-time Graflex camera, the LED lights from a 1970s era calculator, and a windshield wiper blade cut into pieces are all of the components that were used to make the original 1976 version of Luke Skywalker's lightsaber. So they just pulled the flash off the top of that. They took the LEDs out and placed them there. They cut this windshield wiper blade into sections and then they glued them around the edge, and now we have a lightsaber. How cool is that? Well, that's all I got for today, folks. Have a good day. Bye.